Today's graph's going to be on something called integrated rate laws. So what we've done so far have been differential rate laws, where we're looking at concentration and rate. So, so far we've been looking at, right in the rate expression, where the rate of the reaction in change in molarity per time, per second, per minute, whatever it is. So how much is the molarity changing of things? Is the substance going from 1 molar down to 0.3 molar in 5 seconds? Equals K times the concentration of your reactants to a certain order, okay, to a certain power. So in this case, we can look at, okay, how does changing the concentration of the reactant or reactants affect that rate? But it has nothing to do with time. It doesn't tell you about like, hey, this is going to take 7 minutes for this to happen. It's going to take 4 seconds for this reaction to happen, or this much to change. So we have something called integrated rate laws, which they've done a little calculus to determine these. We're going to go through the calculus involved in that. Some integrated rate laws that tell you how concentration and time are related. So we change the concentration of this reactant, reaction takes this time. Change the concentration to this, reaction will take this time. If we want the concentration to change from 1 molar to 0.5 molar, reaction will take this many seconds or minutes. So this will have time involved, these integrated rate laws. And the nice thing about this is really you're just doing a little algebra. The blue sheet's got these reactions on there, so there's your kinetics equations. Okay, so that will be what we're going to use. You'll always have this available for any tests or quizzes, including the AP test. So, first thing, you would need some data. If you had if A is your reactant, okay, so we have a reaction where A is our reactant, or maybe there's multiple reactants, but we've graphed A's concentration versus time. So A is a reactant in a reaction. And if we graph A's concentration versus time, again, if A is a reactant, that concentration is going to go down, okay? If that is a straight line, then we know it's a zero order reaction. If the concentration of A goes down in a straight line. If you graphed concentration versus time and it was some kind of curved line, it would not be zero order. So you're looking for a linear fit, a linear line. So if graphing concentration versus time is linear, then it is a zero order reaction. Okay. And this is written in the form of y equals mx plus b, where obviously m is your slope. I don't know why they have a, but m is your slope. Okay, and they have done this. They said the concentration of A equals negative K times T plus our B-intercept, or our y-intercept. Okay, your y-intercept would be where the concentration of A becomes zero. So this is really our reactant at time T. This is at time zero. Now I don't usually use the equation like that. I usually tend to write it the way it's written on this sheet. Okay, and the way it's written on this sheet is concentration of A, our reactant, at time T, minus the concentration of A initially at time zero. Okay. Ooh, I just had that wrong. I did our y-intercept, sorry. Go back to my graph. I did your x-intercept, sorry. That was not very smart of me. Your y-intercept is going to be here, okay, when time is zero. Okay, so back there, our y-intercept would be that. When we have a concentration at time zero, so ignore what I said, sorry, I'm not thinking very well, equals the negative K times T. So if we think about this a little bit, if we say, okay, if this was initially at 5 molar and it went down to 3 molar, we know our K value. We can solve for time and figure out, okay, how much time did it take to go from 5 molar to 3 molar? Initial at time zero minus there. Or this could be some other time besides time zero. It could be like at 30 seconds. This could be some time later. But always starting amount, finishing amount. Since this is y equals mx plus b, obviously, this is our slope. The slope of this line is equal to our k by negative k. So we could find k by getting the slope of that line if we really wanted to. Okay, we could find it by getting the slope of the line. Again, y-intercept right there. I'm not sure I was thinking that. All right, going on. If we graph concentration versus time and it's not linear, now we graph the natural log of the concentration versus time. So we graph natural log of concentration of a reactant. Okay, this is always a reactant. Graph the natural log of the concentration versus time. If that gives us a linear fit, then it is a first order reaction. Okay, so now it's kind of the same thing here. Y equals mx, so m is still our slope of our line, is still negative k. Okay, slope is still negative k. So we can always get the k value from getting the slope of the line. Sometimes you have to do that. And again, you want a linear line. If this is not linear, it's not first order. If natural log concentration versus time is not linear, it's not a first order reaction. And our y-intercept up here would be our starting amount. Okay, this again, our concentration of A is decreasing as the reaction goes. Okay, decreasing as the reaction goes. Again, I tend to write this like this. I tend to write it as ln of A at time t, just sometime later than that, minus ln of our reactant starting equals negative kt. That's how I tend to use that. Okay, I tend to use that. Oh, I forgot to talk about half-life. So half-life is the time it takes for half of the substance to be gone. So if we go from 1 molar to 0.5 molar, how much time did that take? From 0.5 molar to 0.25 molar, that's half that. How much time did that take? Okay. A first order reaction. Okay, first order reaction has a consistent half-life. Only a first order reaction has a consistent half-life. So its half-life is the same time over and over and over again. If it's 5 minutes the first time, it takes 5 minutes again to get half of it cut off. It takes 5 minutes again to get half cut off. So it is consistent for that. And if we plugged in numbers here, if we had some numbers here, we could plug in. We could always plug in and say, okay, well here our initial concentration was 3 molar. Take the natural log of that, and that means, well, half-life means half of it is gone. So at 1.5 molar, I could do that minus that, and get the half-life that way. Or there is a little equation for half-life, 0.693 over k. And 0.693 is actually the natural log of 2. Natural log of 2 is 0.693. The reason being, I don't know how much you know about logs, but writing this minus this is the same thing as ln of 3 over ln 1.5, which is the same thing as ln of 2. Natural log of 2 is 6.693. You don't really need to know that. But you need to know that that is the equation for that. Or you can always plug in, here's my concentration, here's half of it. Plug in my k value, get my time. All right. Very important to know that a first order reaction has a consistent half-life though. It's always the same amount of time. Okay, always the same amount of time for a half-life. If we go back up here, I forgot to talk about this. I don't generally use this equation ever. I only use that one for half-life for first order. For a zero order, I would just plug in. I would just plug in my numbers. I'd say, okay, here's my starting concentration was 10 molar. If it's 5 molar, how much time would that take? Starting concentration was 1 molar. If it's 0.5 molar, how much time would that take? So I tend to just plug in numbers and figure it out from there. All right. Let's go to the last one. So if neither one of these graphs are linear, if concentration versus time has a curve to it, and natural log concentration versus time has a curve to it, that means we now graph 1 over the concentration of our reactant versus time. If that is linear, that means it is a second order reaction. So we're always looking for the linear line with the graph there. This line is going up because now we're doing 1 over the concentration, which this number is getting smaller and smaller and smaller. So 1 over it is getting bigger. So the slope of this line just equals k. That would be our k value. Again, y equals mx plus b. Tend to write it again as concentration of A at time t minus the concentration of our reactant starting times 0 equals kt. So in this case, our k is a positive value. Okay, so you have to kind of remember that. But not a consistent half-life here. This half-life will change. Just like a zero order reaction, the half-life will change. Okay, it will not stay the same amount of time. First order reaction, the half-life stays the same amount of time as we're doing things. All right, that's kind of the first part of this. I'm gonna stop that and make a new video for the next section of this.